Good evening, students. This video is all about F block elements. The F block elements are also known as inner transition elements. So these are the elements in which they have incomplete d orbital of the penultimate shell, also incomplete f orbital of the anti-penultimate shell. That means n-1 shell consists of incomplete d orbitals and n-2 shell consists of incomplete f orbital. So these are known as inner transition elements. Okay, in addition to incomplete d subshell, their f subshell is also incomplete. As there are 7 f orbitals in a given shell, as much as 14 electrons can be occupied in a given f block series. That is, in a particular f block series has 14 elements. The general electronic configuration of f block elements is written as n-2 f1 to 14, n-1 s2, n-1 p6, n-1 d 0 to 1, and ns2. The F block elements are subdivided into two series named as 4f and 5f. If the differentiating electron enters 4f orbitals, it is known as 4f series and named as lanthanides, and if differentiating electron enters 5f orbitals, it is known as 5f series, which are named as actinides. That means the elements that are following lanthanum in 4f series are known as lanthanides, and the elements that are following actinium in 5f series are known as actinides. So coming to the general characteristics of lanthanides, we have chemistry of lanthanides, electronic structure or configuration, oxidation states, lanthanide contraction and its consequences, which is related with atomic radii, and the last one is magnetic properties. Okay, so in the next slide we can study about the chemistry of lanthanides. So this table shows the lanthanides and actinides. Okay, from lanthanide starts from 57 lanthanum and ends with 71 lutetium, whereas actinides starts from actinium 89 and ends with lawrencium. And the details of the elements will be seen in the while studying about electronic configurations. Okay, coming to the chemistry of lanthanides, actually the lanthanide series consists of only 14, as the lanthanum is included here in F block, which is a D block element. Because of the chemical similarities, it is included in F block elements. So totally we have 15 elements for lanthanides. So they are very good conductors of electricity. They give hydrides and carbides, and they liberate hydrogen from dilute acids. Also they form oxides and hydroxides in the form of M2O3 and MOH thrice. So this is about the chemistry of lanthanides. Coming to the important property, that is electronic configuration. The electronic configuration of lanthanides is not known with certainty. The reason being the fact that 5d and 4f electrons, they are very close in energy. There is very minute difference between the energy levels of 5d and 4f orbitals. So it's not always possible to find out whether the electron is entering 4f orbital or 5d orbital. Because of this, we have two views for the electronic configuration for lanthanides. Okay, so this can be studied here. So the general electronic configuration is written as 1s2 2s2 2p6, 3s2 3p6 3d10, 4s2 4p6 4d10 4f14, 5s2 5p6 5d, and 6s2. Okay, here we take the noble gas configuration, that is xenon, its configuration for lanthanides, followed by 4f 5d and 6s orbitals. And so the atomic number of xenon is 54. And after that the filling of electrons will be given to 4f orbital, 6s orbital and 5d orbital. Here we have two views in the tabular form. For if we take for lanthanum, actually the f orbital starts filling its electrons. From cerium onwards, there is no electron in f orbital for lanthanum. So that is why it is written as 4f0 for lanthanum. And coming to cerium, the second view, coming to the lanthanides, the second view is the most probable view, and it is the most accepted view, where the 5d orbital remains vacant and the electron enters a 4f orbital. So for cerium, two views are given, and the most acceptable xenon 4f2 6s2, and for praseodymium it is 4f3 6s2, neodymium it is 4f4 6s2, promethium 4f5 6s2, samarium followed by 4f6, europium 4f7. And for coming to gadolinium, for the point of extra stability for half-filled orbitals, the electron enters into the 5d orbital. That is why for both the views it is giving the same configuration, that is xenon 4f7 6s2 5d1. And the next, as usually terbium, it has 4f9, because 2 and 8 numbers are missing for the lanthanide configuration. You have to remember this trick. 2 and 8 will be missing. 2 and 8 will be missing. So actually the f orbital starts filling from cerium. So xenon 4f1 5d1 6s2, it is written as xenon 4f1 5d1 6s2, and actually 2 will be missing, and we go for praseodymium xenon 4f3 6s2. In the same way, we cannot write the 4f8 for lanthanides. Instead we get for gadolinium it is 4f7 for the extra stability of half-filled orbitals. Terbium we do not write 4f8, we write only 4f9. Okay, and again dysprosium 4f10, holmium it is 4f11, erbium 4f12, thulium 4f13, ytterbium 4f14, and lutetium, as all the orbitals of f orbital are filled, the extra electron will enter the 5d orbital. That is why its configuration is written as xenon 4f14 5d1 and 6s2. So this is about the electronic configuration. And coming to the oxidation states, the most stable oxidation state of the lanthanides is +3. Unlike d orbitals, these lanthanides show very less number of oxidation states, whereas in d block elements we have variable oxidation states. But most of the lanthanides, their stable oxidation state is +3, and very few elements they go for +2 and +4 oxidation states. Okay, so lanthanum it is +3. So here we have given the configuration for metal, and 2+ oxidation state and 3+ oxidation state. So the electrons will be lost first from the outer 6s orbital, and then they go from 5d and 4f orbitals. So lanthanum we have 5d1 6s2 actual configuration, 4f0, xenon 4f0 5d1 6s2. So the 3 electrons will be lost from first 6s0, and then 5d also becomes 0. Coming to cerium, it is exhibiting +3 and +4. So we have metal is having 4f2 6s2 configuration, so 2 electrons will be lost from 6s orbital, so it has become 6s0, and the other electron from f orbital, so it is written as 4f1 6s0. So in the same way, the following electrons, their oxidation states is written. Okay, for praseodymium it is 4f2 6s0 +3. So +4 is not given. Neodymium is exhibiting +2 oxidation state, +3 and +4, and samarium also it is exhibiting +2, europium +2 +3. And the thing is that lanthanum shows only the +3 oxidation state, which is a characteristic and most stable oxidation state of all the lanthanides. Okay, and coming to gadolinium and lutetium, they form tripositive ions. Here see gadolinium +3, and sorry for the disturbance. So here Coming to oxidation states, gadolinium we have +3, and also lutetium also showing only +3. That means gadolinium and lutetium forms only the tripositive M3 plus ions, because the removal of these 3 electrons gives a stable half filled and completely filled configurations, that is 4f7 and 4f14. Thus any oxidation state other than +3 does not occur in these 2 elements. That is, for gadolinium and lutetium, they are exhibiting only tripositive oxidation state, that is M3 plus. Okay, so the removal of these 3 electrons will be giving the stable oxidation state for half filled and completely filled configurations. Okay, also we can see that the other elements are exhibiting +2 and +4 oxidation states, and it is associated with empty, half filled or completely filled 4f subshells. We can see from the next slide here. See, in addition to the +3 oxidation state, very few lanthanides are exhibiting, they are showing +2 and +4 oxidation states, and it is associated with empty, half filled or completely filled 4f subshell. For example, if we take cerium +4, which is having F0, that is empty, and if we go for europium +2, it has F7. When we take ytterbium +2, it has F14. That's fine, and there are few exceptions for this also. For if we take samarium 2+, it has F6, and thulium 2+, it has F13, and they cannot be explained because of extra stability due to half filled or completely filled, and it is due to some other reasons like thermodynamic and kinetic factors. Okay, so this is about the oxidation states of lanthanides. And coming to the very important property or the concept, that is lanthanide contraction, which is related with ionic radii, as said earlier. So we know that as we move across from in a period from left to right, that is from lanthanum to lutetium, lanthanum 57 to lutetium 71, we know in a period as we go from left to right, there will be a decrease in the size of atoms or ions with the increase of atomic number. Okay, but though there is a continuous decrease in the size of the atoms, the decrease is not regular in case of lanthanides. So this irregular and slow decrease in the size of lanthanides is known as lanthanide contraction. Okay, so why this irregular decrease in size? See, in lanthanides the additional electron enters 4f subshell, but as we move from left to right, we know that there will be increase in atomic number and there will be decrease in the size of the atom, but due to increase in the atomic number step by step, there will be increase in the nuclear charge every step. Okay, so as we move from lanthanum to lutetium, the 4f electrons have to shield the incoming new electrons. The 4f electrons have to shield the incoming new electrons, but the shielding of 4f electron by another 4f electron from the increasing nuclear charge is very little. That is, in one word it can be say that it is imperfect. This imperfect shielding is in turn depends on the shape of the f orbital, which is very much diffused. Okay, because of this imperfect shielding, there is irregular decrease in the size of the lanthanides. Though there is a decrease, it is not uniform, it is irregular. So this irregular decrease of the size of the atoms when we move from lanthanum to lutetium is known as lanthanide contraction. So as the atomic number increases, the nuclear charge increases by each step, that is increases as unity, but there is no proper increase in the shielding effect of already present 4f electrons on the incoming new 4f electrons. This causes contraction in the size of the 4f subshell, but the decrease is not regular. It is seen much in first 6 elements of the lanthanides, and this is known as lanthanide contraction. Okay, so because of this lanthanide contraction, there are a few more effects that is seen in the properties of lanthanides and post lanthanides. Okay, the three important consequences. In this slide, we can see the three important consequences of lanthanide contraction. They are occurrence of yttrium with heavier lanthanides, second one is basicity differences, and third one is anomalous behavior of post lanthanides. So, when we come to the first point, that is occurrence of yttrium with heavier lanthanides. Yttrium is a D block element, but it is seen, it is occurred in nature along with the lanthanides. Why? Because the size of yttrium 3 plus ion is almost same as the terbium, dysprosium, holmium. Yttrium occurs with lanthanides in natural minerals. Also, the other properties like crystal structure, solubility, and chemical properties are very close to heavier lanthanides, and that is why these lanthanides are called as yttrium earths. Yttrium earths, because of the occurrence of yttrium with heavier lanthanides, these lanthanides are known as yttrium earths. It is not clearly seen in the slide. If you want, you can note it. Okay, so this is the first consequence because of the lanthanide contraction. So that is occurrence of yttrium with heavier lanthanides. Why it is occurring with heavier lanthanides? Because of its size. Due to lanthanide contraction, there is no proper decrease in the size of the lanthanides. They can be seen with the size of the D block elements. Yttrium is having the tripositive yttrium ion. Its size is same as the terbium 3 plus, dysprosium 3 plus, holmium 3 plus. The yttrium occurs with lanthanides in natural minerals. Also, the other properties like solubility and other chemical properties, also the crystal structure seems similar with the lanthanides. That's why lanthanides are known as yttrium earths. Okay, coming to basicity differences, we know that the basic strength of the oxides and hydroxides decreases from lanthanum to lutetium. That means when there is increase in the atomic number, the basic strength of the oxides and hydroxides decreases. That is why for lanthanum hydroxide is the most basic, while the lutetium hydroxide is the least basic. And again, this is because of the lanthanide contraction. As the size across the period, as the size of the atomic number increases and the size of the ionic size also decreases. So when we go from lanthanum to lutetium, the lanthanide cation size decreases. Because of that decrease in size of the lanthanide cations, there is increase in the covalent character and decrease in the ionic character between the lanthanide ions of oxides and hydroxides ions. Thereby it reduces the basicity from lanthanum to lutetium. That is why lanthanum hydroxide seems to be most basic, while lutetium hydroxide is the least basic. Okay, and understand. So what is the basicity? What is the consequence of lanthanide contraction? Second consequence is the basicity difference. We know that as we move from left to right across a period, that is from lanthanum to lutetium, the atomic number increases and the basic strength of the oxides and hydroxides of lanthanides decreases from lanthanum to lutetium. That is why lanthanum hydroxide is the most basic, while lutetium hydroxide is least basic. Okay, here as we move from lanthanum to lutetium, the covalent character increases and the ionic character decreases between the metal and its oxides and hydroxides. Okay, that's why there will be seen a decrease in the basicity of these oxides and hydroxides. And the last and third consequence is the anomalous behavior of post lanthanides. That means abnormal behavior of the post lanthanides, which is deviating from the normal characteristics. So coming to the post lanthanides, so actually what are the post lanthanide elements? That means the elements that are following the lanthanides are known as post lanthanides. We can see in the next slides the post lanthanide elements, or they can be hafnium to gold, hafnium tantalum, tungsten, rhenium, osmium, iridium, platinum, gold. They are following the lanthanides, that is they come after the cerium to lutetium, that is after lutetium 72 hafnium is the element. So the elements that are following the lanthanides are known as post lanthanide elements, and we can see some anomalous behavior in these post lanthanides due to lanthanide contraction. Okay, usually when we go down the group from top to bottom, the atomic size or ionic sizes increases. Okay, so this we can clearly see from third A group, that is scandium, yttrium and lanthanum. We can see a consequent increase from scandium to lanthanum. Scandium 1.64, yttrium is 1.80 and lanthanum is 1.88. But when we come to the post lanthanide elements, we can see a very minute difference in the increases from 4D series and 5D series of D block elements. We can see there seem to be almost similar, the atomic sizes. That is zirconium, it is from titanium to zirconium, we can see a little increase, that is 1.45 to 1.59. But coming to zirconium and hafnium, that is not the case. It is very similar, that is 1.59 to 1.56. When we come to niobium and tantalum, it's almost same, 1.43 and 1.43. So we can see this anomalous behavior, that is when we go down from top to bottom in a group, there should be a gradual increase in the atomic or ionic radius of the atoms, but it is not so in the case of post lanthanide elements. We can see the cases of zirconium, hafnium, niobium, tantalum, molybdenum, tungsten. This is the consequence of the lanthanide contraction. Okay, and the next property is the last one, that is magnetic properties. So we know the D block elements, most of them are paramagnetic and very few are diamagnetic. Here also, what is diamagnetic and paramagnetic? Ions containing paired electrons are known as diamagnetic, and those with unpaired are said to be paramagnetic. In lanthanides, lanthanum 3 plus, that is 4f0, and lutetium 3 plus, 4f14, they have no unpaired electrons, they are said to be diamagnetic, that is they exhibit diamagnetic behavior, because lanthanum, tripositive lanthanum and lutetium ions 4f0 and 4f14, this is empty and that is completely filled, having no unpaired electrons, are said to be diamagnetic. All other tripositive lanthanide ions are paramagnetic, except lanthanum and lutetium. All other tripositive lanthanide ions are paramagnetic. Okay, the reason that here the 4f electrons are well shielded from the external fields by the overlying 5s and 5p electrons. Coming to the magnetic moment, calculation of magnetic moment, for lanthanides, the total magnetic moment is equal to both spin and orbital magnetic moments, because here the 4f electrons are well shielded from the outermost orbitals like 5s and 5p. They won't interact with the outermost atmosphere. So the orbital magnetic moment is not affected as in the case of D block elements. So here the total magnetic moment is calculated from both the spin and orbital magnetic moment. Okay, so this is about, so mu is equal to, mu is magnetic moment, it is calculated from mu L and mu S. Mu L is orbital magnetic moment and mu S is spin magnetic moment. Because the 4f electrons are lying innerly, the outermost orbitals, that is 5s and 5p, they shield the 4f electrons or 4f orbital from the outermost atmosphere, so the orbital magnetic moment cannot be quenched, just as in the case of D block elements. So hence in 4f elements, total magnetic moment is calculated by taking into consideration both orbital magnetic moment and spin magnetic moment. So mu is equal to mu L plus mu S. So this is all about lanthanides, that is 4f series elements. And next, coming to the general characteristics of actinides. So the general characteristics are same as in lanthanides, that is chemistry of actinides, electronic structure or configuration, oxidation states, actinide contraction and its consequences, and magnetic properties. Okay, and so The elements with atomic number 89 to 103 in which 5f orbitals are filled are known as actinide series. In actinides, the anti-penultimate shell 5f orbital is filled, and thus actinides are called as second inner transition series. Only first four elements of this series, that is actinium, thorium, protactinium, uranium, occur in nature. The other elements are made artificially with nuclear bombardment. Okay, so only the actinium, thorium, protactinium and uranium are naturally occur, and the other are man-made artificial elements from actinide series. So coming to electronic configuration, here also we have two views, and they are named as Seaborg view and Dawson view. The reason is the same. Here 6d orbitals and 5f orbitals are all of almost equal energies. Because of this controversy, we have two views. One from Seaborg view, the 5f orbital starts filling at thorium, while according to Dawson view, the 5f orbital starts filling at neptunium. Okay, this is somewhat different from lanthanides. So according to Seaborg view, the 5f orbital starts filling from thorium, while according to Dawson view, the 5f orbital starts filling from neptunium. So when we see the Seaborg view, here radon, so it's as in the case of lanthanides, we took xenon. Here radon is given, so radon, and the next is 6d 0 to 2 and 7s2, and 5f orbital is starts filling. So radon, its electronic configuration is 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 4d10 4f14 5s2 5p6 5d10 6s2 and 6p6. Okay, so actinium, it consists of radon 61 7s2. Here 5f becomes 0, and thorium, it is radon 5f1 6d1 7s2, and protactinium, it is 5f2, uranium 5f3, neptunium 5f4, according to Seaborg, neptunium 5f4 and plutonium 5f5. Here also, for extra stability of extra stability for half filled orbitals, americium, we have 5f7 and 7s2, no d orbital here, and next is curium 5f7 and berkenium 5f8, californium 5f9, instanium 5f10, fermium 5f11, mendelevium 5f12, nobelium 5f13, lawrencium 5f14, 6d1 7s2. Okay, so this is according to Seaborg. And coming to Dawson view, we have for actinium, it is only radon 6d1 7s2, and thorium, here also radon, but 5f is not filled. Here also it is 5f0, so the electron enters into 6d orbital, so it is given as radon 6d2 7s2. Protactinium, it is radon 6d3 7s2, and for uranium, it is radon 6d4 7s2, and from here onwards, from neptunium, we have radon 5f4 6d1 7s2, and it continues from neptunium to lawrencium. For plutonium, it is 5f5, americium 5f6, curium, it is 5f7, and berkenium, it is 5f8, californium, it is 5f9, instanium, it is 5f10, fermium, it is 5f11, mendelevium, it is 5f12, nobelium, it is 5f13, lawrencium, it is 5f14. So this is how the Seaborg and Dawson view, it is completely different from that of lanthanides. Whereas in here in actinides, 5f orbital starts filling from the second element, that is thorium, in Seaborg view, whereas from Dawson view the 5f orbital starts filling from neptunium. Okay, so this is how we have to write the electronic configuration. And coming to the oxidation states, actinides show variety of oxidation states. There is a little similarity between d block elements and actinides, because here also we can see a variety of oxidation states. Uranium shows oxidation states from +3 to +6, whereas neptunium and plutonium shows oxidation states from +3 to +7. But the principal oxidation state of actinides are +3 and +4, whereas in some other cases +2, +5, +6 are most important. And +3 is the most stable oxidation state for actinium, americium and all the elements following them. And +4 is the most stable oxidation state of thorium and plutonium, and +2 in nobelium, +5 in protactinium and neptunium, and +6 in uranium. Okay, this you have to remember. A little confused about oxidation states, so we can see a variety of oxidation states for all the elements. Once again repeating the same. So actinides will show variety of oxidation states, that is uranium shows oxidation states from +3 to +6. Neptunium and plutonium, they show from +3 to +7, but the principal oxidation state of actinides are +3 and +4, and in some other cases +2, +5, +6 are considered as most important one. And +3 is the most stable oxidation state for actinium, americium and all the following elements. Okay, that is curium, berkelium, californium and all the following. And +4 is the most stable oxidation state for thorium and plutonium, whereas +2 in nobelium, +5 in protactinium and neptunium, and +6 in uranium. Okay, so +3 is the most stable oxidation state for actinium, americium and all the rest of the elements, whereas +4 is the most stable oxidation state for thorium and plutonium, +2 is the most oxidation stable for nobelium, +5 is the most stable oxidation state for protactinium and neptunium, and +6 for uranium. Okay, so this is about oxidation states for actinides. And coming to the actinide contraction, so this is similar to lanthanide contraction. In actinides, the atomic radius decreases with increasing atomic number when we go from actinium to lawrencium. This is known as actinide contraction. Because of the imperfect screening of the 5f electrons by the increasing nuclear charge, this actinide contraction is seen much more than in lanthanides here. Okay, this in turn is due to the lower shielding of 5f electrons, which are pulled more strongly by the nucleus. Okay, here the imperfect shielding of 5f electron is seen much more than the 4f electrons of the lanthanides. That's why the nucleus will attract the 5f electrons more, so they are pulled more strongly by the nucleus, and there is much more decrease in the size of the actinides. Okay, although the actinide contraction is similar initially as that of lanthanides, the elements from curium onwards means the second half are very smaller than expected. This is due to the poor shielding effect of the already the first 5f electrons in actinides than 4f electrons in lanthanides. This actinide contraction leads to the decrease in basicity of the elements with increasing atomic number. That's why actinium oxides and hydroxides, they are most basic than the lawrencium oxides and hydroxides. Okay, this is a consequence of the actinide contraction. And next property is comparison between lanthanides and actinides. Comparison between lanthanides and actinides. So magnetic properties are similar to that of lanthanides, that is actinides also, the show some of them show diamagnetic and very few show paramagnetic behavior. And coming to the calculation of magnetic moment, we consider both orbital and spin magnetic moments as a total magnetic moments. Okay, now coming to the comparison between lanthanides and actinides, the comparison can be of two types. That means we can find out the similarities, also the differences. So coming to the similar properties, lanthanides and actinides have the predominant oxidation state as +3. In both the series, f orbitals are filled, that is 4f in lanthanides and 5f in actinides. Both show decrease in atomic size with increase in atomic number. Both have low electronegativity, but they are very reactive. The nitrates, perchlorates, sulfates of actinides and lanthanides are soluble, while hydroxides, fluorides and carbonates are insoluble. That means nitrates, perchlorates, sulfates of actinides and lanthanides are soluble, whereas the hydroxides, fluorides and carbonates of actinides and lanthanides are insoluble. Actinides like lanthanides show ion exchange behavior. Because of this ion exchange behavior, the mixture of lanthanides and they can be easily separated by using this ion exchange technique. So these are the similar properties of lanthanides and actinides. And coming to the differences, so lanthanides, the additional electron enters a 4f orbital, whereas in actinides it enters 5f orbital, and 4f electrons have more shielding effect, whereas 5f electrons have poor when compared to actinides, lanthanides will have more shielding effect and 5f electrons will have poor shielding effect. That's why actinide contraction is much more seen in actinides than in lanthanide contraction. And maximum oxidation state of lanthanides is 4, whereas in actinides it is +7. And lanthanides, they do not form any complexes, they don't have the tendency to form complexes, whereas actinides, they have the tendency to form complexes very easily. That's why actinides, they have similarities with d block elements also. And other differences, except promethium, all the other are non-radioactive, but actinides, all of them are radioactive. And lanthanides, they are less basic, whereas actinide compounds are more basic. Most of the lanthanides are colorless and they show paramagnetic, whereas actinides are colored and paramagnetic. And lanthanides, they don't form any oxocations, whereas actinides form oxocations like uranium, plutonium, neptunium, they form oxocations as given in the table. Okay, so this is about f block elements and the characteristics of lanthanides, actinides, and the most important property, lanthanide contraction and actinide contraction. So thank you students. If you have any doubts, please mail to me. If you, after listening, please don't forget to like and subscribe this video. Thank you all.